Yes.
Oh, thank you. So yes, as Caleb said, I'm going to be going over some of the clustering methodology that is going to make its way into DESI. All right, so what is the motivation? Basically, why are we doing this? So as Mike already kind of touched on, the NBM is increasingly being used as the starting point for NWS forecasts. And the NBM does a good job of blending a large volume of forecast data into an accurate and actionable forecast, but it's kind of a black box. And forecasters crave more information on what went into the NBM. They also want information on forecast uncertainty in space and time that the NBM doesn't necessarily provide. And they need tools to give them this information. So that's kind of the meteorological problem. So an impractical solution to this would be obviously for a forecaster to look at all of the inputs that went into the NBM. So just to kind of illustrate this, I have a plot showing all 100 ensemble member forecasts for 500 millibar heights over the Western US on day 6. And again, this is just not a practical solution because yes, you can look at it, but it's very hard to see any discernible signals when you're looking at so much data. An overly simple solution would be to calculate an ensemble mean for each ensemble prediction system and then sort of treat them as the possible forecast scenarios. And this is traditionally what's been done. And the benefits of this are that it's simple and lets the forecaster somewhat see the underlying data that went into the NBM. But the drawbacks are it doesn't adequately show the range of possible forecast outcomes, and it assumes that the biggest determinant of an ensemble member's forecast is its parent model, which isn't really a valid assumption. And to just kind of demonstrate this, I have the means from the Canadian, the GEFS, the European, as well as the multi-model mean for this same case upcoming in the Western US. And again, if you look at them quickly, they all look pretty similar. There's not much difference. So what's a better solution? Well, a better solution is ensemble clustering, because ensemble clustering partitions the members of an ensemble into groups of members that have broadly similar forecasts. So in other words, discrete forecast scenarios. By simplifying the ensemble down into a few clusters, it allows the forecasters to dig more into the data and get more complete information about forecast uncertainty in both space and time without that data overload problem. So to assist forecasters in their creation of medium range or day 3 to 7 forecasts, WPC developed an ensemble clustering tool, and DESI will be the new home for this tool. So ensemble clustering, how do we go about clustering? Well, DESI, as the WPC ensemble clustering, will use a version of ensemble clustering that's known as fuzzy clustering. And basically, fuzzy clustering has a 3-step recipe. The first step is to evaluate and interpret the first 2 empirical orthogonal functions, or EOFs, of a relevant ensemble forecast variable over a region of interest. Step 2 is to use k-means clustering on the principal components for the EOFs to create clusters of similar members. And then finally, the most important step is to view the clusters. All right, so the specifics of the DESI fuzzy clustering method. So for now, the ensemble data sets we're using are the half-degree resolution versions of the global ensembles, which we have are the Canadian, the GEFS, and the European. Now, as was said earlier, we are eventually probably going to migrate to using the higher resolution data that MDL can provide. But for now, just for this proof of concept, we're using the half-degree resolution version because that's what we have available to us. So the relevant variable for EOF analysis will be 500 millibar heights. Now, we've chosen 500 millibar heights because it's a very good summary variable. And if you had to make a forecast based on one variable alone, it would probably be 500 millibar heights, because that can do a good job of telling you where temperatures are going to be relatively cold or warm versus normal, and also if there's going to be precipitation or if it's going to be dry. So the regions of interest are several domains over the CONUS, including domains for the Western US, and then smaller domains, including the Northwest and the Southwest. And then how many clusters? Well, generally 2 to 5 is good. So what we do is we run k-means clustering on the EOF principal components with 2, 3, 4, and 5 clusters. And then we use the silhouette score to determine which of those numbers is the optimal number of clusters. And I'll go a little more into detail with that in a little bit. So for an example, let's just apply fuzzy clustering to today's 6-day forecast over the Western US. So the first step in the process is to calculate and interpret the first 2 EOFs. So what are EOFs? They're a data analysis technique that is often used in climate studies as a method for determining the spatial patterns that most efficiently explain the variability of a multivariate data set. So in other words, what patterns are most common in the data set? And it's how we get teleconnections like the NAO, which is just the first EOF of sea level pressure over the North Atlantic in winter. EOFs that are calculated across the model ensemble member dimension, as opposed to that more conventional time dimension, result in modes that show the dominant patterns of difference between individual ensemble members and the ensemble mean. And for each EOF, each ensemble member will have what's called a principal component. So what are principal components? The principal components are the projection of the dominant EOF patterns onto the difference between each of the ensemble members and the ensemble mean. So an English translation of that is that an ensemble member with a large principal component for an EOF pattern will resemble the ensemble mean with the EOF pattern either added or subtracted to it. And whether you add or subtract is determined by the sign of that principal component. So it's a lot of math, but you don't really need to know the math in order to interpret and imply the results of the EOF analysis. So for our example, we're going to be calculating the EOFs of 500 millibar heights over the Western US on day 6 from the ensembles that were initialized this morning. All right, so here we have the first two EOFs, and this is just a screenshot from DESI, so this is not on the WPC clustering website. So we can see the first two EOFs, the first one on the left and the second one on the right. In each of these panels, what's contoured is the multi-model ensemble mean, and then the shading is the actual EOF pattern. This first EOF pattern explains 54% of the variance in the 500 millibar height field for the ensemble for this particular time. And we can see that the EOF pattern is kind of highlighting this area over the southwest. So basically what the EOF is telling us is that there's a lot of uncertainty in this forecast over the southwestern US. And if we look at the multi-model ensemble mean pattern, we can see that there's a trough right around that area with ridging kind of off the western US. So what this is telling us is that some ensemble members have much higher heights than the multi-model ensemble mean here, and some have much lower, with those having much higher heights having this ridge building in faster, and those having lower heights here having this trough kind of hang around a bit longer. So what this is telling us is that EOF1 represents how fast will that trough pull out and the ridge build in. Looking at EOF2, which explains about 25% of the variance, we can see that another area of uncertainty is offshore the Pacific Northwest. And basically, there's already a ridge here. So what this is telling us is there's uncertainty in the degree of ridging in this location. All right, so basically, each ensemble member will have a principal component for the first two EOFs. And what you can do is you can plot these principal components in a phase space with principal component for EOF1 along the x-axis, principal component for EOF2 along the y-axis. And basically, we have plotted all 100 ensemble members in this PC1, PC2 phase space, and we've already grouped them into clusters, but just kind of ignore that for now. So to come up with a physical interpretation for what kind of each area of the phase space looks like, we can relate the EOFs with the principal components. So in this part of the phase space, the principal components for EOF1 are positive. So what we're essentially doing is adding this pattern onto the multi-model ensemble mean. So essentially, we're lowering the heights over the southwest. So this part of the phase space, or members that are in this part of the phase space, are the members that have that trough hanging on a bit longer. Going to this part of the phase space, these are the members that have a principal component for EOF1 that's negative. So in other words, you are subtracting this pattern from the multi-model ensemble mean. So essentially, since you're subtracting a negative pattern, you would have the effect of raising the heights here. So the models or the ensemble members that are in this part of the phase space have that ridge building in faster. And then you can do the same sort of analysis for EOF2, which is along the y-axis. So then what you do is you can apply k-means clustering to that phase space to kind of group members that are broadly similar together. So what is k-means clustering? It's an algorithm that groups two-dimensional data to minimize distance between each point and the center of the cluster it is assigned to. So the number of clusters needs to be specified beforehand, and usually 2 to 5 clusters is appropriate. So to select the optimal number of clusters, we run k-means clustering on the EOF principal components to create 2, 3, 4, and 5 clusters. And then the number of clusters that produces the highest average silhouette score is selected. And the silhouette score is just a measure of how similar an object is to its own cluster versus the other clusters. And generally, a higher score is better. All right, so again, you have the phase space with the principal components for EOF1 along the x-axis and the principal components for EOF2 along the y-axis, and you can apply k-means clustering to this phase space. And on this particular date, we come up with 3 clusters. We have cluster 1 here, which is kind of down in this part of the phase. So the thing that these members have in common is that their principal component for ELF2 is negative. So the physical interpretation for cluster 1 is that there's more ridging over the northwest. And on the side here, we have figures that show the cluster mean for each cluster, as well as how it differs from the multi-model ensemble mean. And again, along the top of each panel, it just kind of gives you a sense of the support it has. So cluster 1 in this case has 41% of the total ensemble, so 41% of that 100 ensemble members. And indeed, we can see that, you know, comparing the difference from the multi-model mean, it does have more ridging over the northwest. Looking at cluster 2, they're in this area of the phase space. So the physical interpretation for cluster 2 is that trough hangs on longer with less ridging over the northwest. And that's indeed what we see in the difference panel on the side here. And then finally, cluster 3 is over in this part of the phase space. So the physical interpretation for cluster 3 is that ridge builds in faster, but less ridging over the United States. So that's all well and good, and that's how we arrive at the clusters. But to actually use the clusters, you don't really need to go through that. And if you don't have the time, you don't have to. Because the physical interpretation for each cluster becomes very obvious when, obviously, you view the clusters. So we can see cluster 1 clearly has that more ridging over the northwest. Cluster 2 clearly has that trough hanging on. And cluster 3 clearly has that ridge building into the southwest a bit faster. And what we can then do is, you know, take the clusters that are based off of the 500 millibar heights and then look at other variable forecasts that are based off of these 500 millibar height clusters. And that's what I have here. Here is the 2-meter temperature forecast. And again, what we're shading is the difference from the multi-model ensemble mean. And if you relate it back to the 500 millibar heights, it makes sense. So we'll just quickly look at cluster 3, which has higher heights over the southwest and lower heights over the northwest. It makes sense that this cluster's temperature forecast is warmer over the southwest and a bit cooler over the Pacific Northwest. So that's an overview of our clustering methodology. I just wanted to end with some verification. So one of the things we've been trying to do more recently is to establish, you know, is this clustering beneficial? So, and also, does the best performing cluster consistently outperform the best performing ensemble mean or deterministic forecast? So what I've done is I've used paired verification, and I've compared the best performing cluster from each day to the best performing ensemble mean and deterministic model. And this is over a period of 6 months. And the results are shown in this figure here. So we have day 3, day 4, day 5, and out through day 7. The best performing ensemble cluster is in blue, the best performing ensemble mean is in yellow, and the best performing deterministic is in green. And this is for mean absolute error of the 500 millibar height pattern. So basically how you can read this figure is, well, clearly at each day, the best cluster has lower absolute error than the best performing ensemble or the best deterministic. And what these error bars shows is the statistical significance of this result. So basically, when you have a bar going completely over this error bar, that means that the best cluster was statistically significantly better than either the best ensemble or the best deterministic. So we can see basically at every day from days 3 to 7, the best performing cluster outperforms the best performing ensemble mean or deterministic model, and this result is statistically significant. And another thing I want to point out about this figure is if you look at day 3, the differences are pretty small. But as we go out in time to day 7, the differences between the best performing cluster and the best performing ensemble or deterministic model become much more significant. And this is just kind of lending credence to the idea that clustering really is most beneficial the further out in time that you go. So just to quickly summarize, the EOFs show the dominant modes of uncertainty in the forecast, and ensemble clustering using the EOFs does a good job of quickly showing the possible alternative forecast scenarios to that most likely scenario. So the use of silhouette score we use the silhouette score to allow the number of clusters to vary, and that is one difference from the WPC clustering page as it is now. On the WPC page, there's just 4 clusters every day. Also, clustering will be available for days 1 through 9, whereas right now on the WPC page, it's just days 3 through 7. One thing I will note is if the spread in the forecast is low, so in other words, clustering won't be helpful, DESI will only return 1 cluster, and that's the multi-model mean. And this is pretty common on days 1 and 2. So that's all I had, and now I will probably pass it over to Travis, who will give a better overview of DESI and its functionality.